chapter 7. It's the homework, and I was like, oh my gosh, it's already past 6. Sorry about that. I want to point out that we've done chapter 7.1. And just a reminder, like this is like just like chapter whatever the last one was, 4, where I did part of it and then we went back and did the rest of it. Same kind of thing. Okay, so chapter 7 is really talking about like how ecosystems heal themselves, which is this idea of succession. That's what it's called. I want to see. So this is our chapter 7 intro slide. And then we have gone all the way through to, is that the right one? One more. Well, there we go. Oh, no, we watched that already. Okay, 7.2. So how do communities and ecosystems respond to changing environmental conditions, especially what we refer to as a disturbance? So not just like slow change over time, but some kind of, it's usually a quicker change. Ecological succession is the normal gradual changing in structure and species composition in a given system. Okay. I guess even over the short time. That's not what we normally think of. We normally think of it as in response to a, like I said, a disturbance. So this idea of succession is like kind of like development in humans. I mean, it's like parallel to that concept of development. I'm trying to move this little guy out of the way. I don't know if you guys can see it, but I can see like my tools is kind of annoying. Primary ecological succession is going to happen at the very beginning of an ecosystem being established. So there's no life. So we're just talking geology. And then from there, how does life develop over time? And we can see this happen. It's in the notes, but that we can see this happen like when volcanic eruptions happen and you just get like a totally wiped out ecosystem. This is kind of a schematic of how we just would start off with rocks and then get what are referred to as pioneer species, then small herbs and shrubs, and then a little bit larger heath mat. It's not a term I was actually familiar with. And then jack pine, black spruce, aspen, those are like examples, like deciduous and a little bit smaller trees. And then finally this very mature forest at the very end where you have all the different vertical layers. You have large tree cover, canopy cover, and a very, what we refer to as, a mature ecosystem. Okay.
Although glacial ice is
I'm going to let you watch that on your own. And I'm going to keep the lecture rolling. So when I post chapter 7, make sure that you watch the time lapse of glaciers, because glaciers would be considered, or the movement of a glacier would kind of scrape all of the soil and all the land away, and it would leave bare rock. And so that would leave us with a change that would open up an area for primary succession to take place. And you can watch each of the videos on your own. And here's another one that's like a kind of, not a time lapse, but a walk through developmentally. This one's really cool. I'll just kind of like pop through, but this is primary succession after
by
volcano.
biotic and abiotic. Ecologist Joe Mascaro.
I don't want her to talk. But you can see that the landscape is going to change, and they're going to walk you through how, what each of those like development levels are called in succession, like early colonizers, like I talked about before, the pioneer species, all the way through to a mature ecosystem, which I can't click over there because my little picture's in the way. But you're going to watch that one as well. It goes through the stages of primary succession. Take notes on it. That one has actual like good information.
Ecosystems are shaped by biotic.
Sorry, it's so hyper. All right. One of the other interesting examples of succession is how we might get a waterway that will build up sediment and how that will change over time. This is lake succession or pond succession. And this is the shifting of one ecosystem into another. So we know that, like I said, okay, my comment at the beginning was totally wrong. Succession is the development of ecosystems and how they change. I would just normally think of just primary and secondary succession, but there's different types of succession. How do ecosystems change? This one is one of my favorites to watch. And then there's another video here for you that goes
There are various
through
types.
all of the different stages of limnetic or pond succession. All right. If there is soil, that is when we're going to see secondary succession, or if it's because of some kind of disturbance, we're going to see secondary succession where the ecosystem is going to bounce back. This is a series, like especially in terrestrial ecosystems, but this is the series of terrestrial communities or ecosystems that will develop in a place that has sediments or soils left behind. Okay, so a burn forest or a cut forest or a flooded area, but there is soil intact. These are the steps that an ecosystem will go through and develop. Factors that affect the rate of succession: facilitation of area by one species or another, and then inhibition hinders growth. Actually, don't know what that is referring to. Inhibition hinders growth. I'm wondering if that means like when you have a bunch of grass and then there's like an overpopulation of rabbits. I would have to look at the text and see what what the example is there. Sorry. All right. This is secondary succession. It looks very much like primary succession, but we don't have the rock formation. And so then you don't have to have the lichens and the bryllophytes and stuff like having to break down the rock. Is there a balance of nature? This is just like in chapter 7, there's a part that you read that talks about kind of this idea that there's this traditional view that ecological succession proceeds all the way to a stable climax community, and equilibrium is called the balance of nature. And then currently we think that succession leads to more complex and diverse, resilient ecosystems, and they can withstand changes if those changes aren't too large or they aren't too sudden. So the traditional view is kind of like it arrives, and the current view is more like it's an ongoing idea of health. Living systems are sustained through constant change. In physics, we learn about inertia. Inertia is this idea that like this that it is a force, right? That an object in motion tends to stay in motion. Well, life has inertia. There's a certain kind of like once life is in an area, there's a tendency for that to continue growing. So the ability of a living system to survive and then to moderate disturbances, we refer to that ecologically as inertia. And then resilience is the ability of a living system to be restored through secondary succession after a moderate disturbance. Different ecosystems, productivity plays into this. And different ecosystems have different rates at which they will bounce back. 7.3 deals with what will limit population growth. Populations, as we've talked about before, are this interbreeding group of individuals. They have to be the same species, but they also have to be interacting and breeding. Population size may do two things, right? Or three things, I guess. It may increase, it may decrease, or it may stay steady in the same and remain the same in response to a changing environmental condition. Scientists use sampling techniques to estimate population sizes, and we're in the midst of that lab. I think that there's one more group that has to do their lab. Population distribution that refers to the concept of like how a population but how they naturally live. So most populations live together in clumps or in groups, and organisms kind of cluster. This makes it easier for them to find resources, to find protection from predators. They live together, they like work together. But not all organisms do that. Okay, but you'll see like, fish like kind of schooling together, or like a forest, all the trees kind of grow in the same area, right? Variables that govern changes in population size, there are 4: birth, death, immigration, and emigration. Immigration in, emigration exit. You can be born into a population, or you can die out of a population, or you can move in from the outside, or you can leave. That's easy, right? Age distribution or age structure is a diagram that we use to take a look at how the ages of a population are distributed. Distribution of individuals among those age groups are going to produce different patterns. In human population, we refer to those groups as pre-reproductive, well, I guess in any population, pre-reproductive, reproductive, and post-reproductive stages, because most organisms aren't born ready to reproduce. There has to be like some maturation, and then they will be ready to reproduce. And then there's a point at which they aren't reproducing anymore. These are examples of different distributions. Clumped distribution, elephants would be an example of that. Uniform, creosote bushes are toxic to each other. They don't like to be next to each other. So you see this kind of strange arrangement of bushes that's very uniform. Penguins are another example of this. They're a little bit territorial. They don't want to be right up against each other. So they'll kind of like set their nests out. And they seem to be evenly distributed in this like weird uniform arrangement. And then random, most of the time we see a lot of plants, or in marine organisms, those like that just kind of like take with the current their reproductive efforts, or like spiders, kind of get taken with the wind, or plants where the seeds will get taken with the wind. That will produce a random population distribution. Oh, I went backwards. Sorry about that. Okay, so in dealing with population sampling, characterizations of populations can be qualitative or quantitative. Quantitative is numbers, just looking at numbers, and qualitative is looking more at the characteristics of that organism. Quadrat sampling, which we will get into like next week when we start dealing more with population, but quadrat sampling can be used to determine abundance, density, and distribution of a species. Those are some of the ways that we talk about like not just biodiversity, but then in digging into that, like how abundant is this species in relation to everything else that is there? How dense is it in relation to the area that we're looking at? Mark and recapture is the sampling method that you're using in your lab. And this is one that we use to estimate the size of a population of a defined area. Mark and recapture has some limitations, and it talks about that in your lab, but like you can't use, it's not really appropriate to use mark and recapture on trees, because I don't know where they're going, right? So it only works for certain populations. Populations can be limited because each population has a range of tolerance. Like polar bears don't live in the tropics, right? There's variation in physical and chemical environments under which organisms do best. They live within a range that works for them. Limiting factors can be the precipitation on land, water temperature, for aquatic environments, clarity, depth, population density itself may be a limiting factor. Maybe there's just too many of this population in the area and competition is too high, and so then population is pressured to move out of that area. You can see that this is a diagram kind of showing like the abundance of organisms they'll have an optimum range, and then like this doesn't apply to all organisms, but you can kind of, or not. It does not this particular characteristic, talking about temperature, right? But you can see there's like an optimum range for temperature for these particular fish, right? And then there's a point at which it's too warm, and you have this zone of physiological stress. A few organisms will survive there, but there's a point at which no organisms are going to be existing in that really high temperature water or the really low temperature water. So there's kind of a distribution. Like averages based on a collection of genetic traits, like how this individual population interacts with the ecosystem. All right, no population can grow indefinitely. We do see that sometimes a population will grow really quickly for a time. Okay, some species can reproduce exponentially. If they reproduce at an early age, if they have many offspring, if there's short intervals between their reproductive cycles, you're going to see this really big spike. It produces what we call a J-shaped curve for growth. It's exponential growth. Examples of this may be bacteria, insects, mice, frogs, and it produces this curve on the left. However, eventually there will be a limit to that growth, and we call that carrying capacity. Limiting factors push back on the population, obviously, like the amount of food, water, whether there's an accumulation of waste, like if it's an aquatic system, is there an accumulation of waste in that pond that now is going to be detrimental to the younger members of that particular population? There's a lot of things that can limit the growth of a population. And so usually we see that organisms will kind of overshoot and then come back, and they will establish what would be a normal population around a carrying capacity. Population growth in nature is always limited by some factor. Environmental resistance is a sum of all the factors that limit population growth. That is a term to learn. Environmental resistance, all the factors together. Carrying capacity is the maximum population that a given species of a particular habitat that can be sustained indefinitely. Often this overshoot results in a little bit of a population crash, and then we may see things kind of even out over time. This graph is a little bit unrealistic. Alrighty. This is looking at a reindeer population. Gives you an example of, we've got carrying capacity well below 500 individuals. However, reindeer numbers shot up in the 1930s. Let me see, what's the story following. They were introduced. So after a population of reindeer was introduced into the small Bering Sea island of St. Paul in 1910, there was no real limit. So you see that there was exponential growth for a while, and then we have this massive crash, and then probably if the population is still present, then it's usually it's oscillating kind of at a set normal. We have talked about these reproductive patterns before, but we want to get them noted down. Different reproductive patterns are going to play into population numbers and population growth. Are selected species are you're going to focus on the rate, population or reproductive rate. This species has a capacity for high rate of population growth because they have a high reproductive rate. Algae, bacteria, frogs, most insects, many fish, many will go through irregular or unstable cycles in population sizes. You'll see large fluctuations, but usually that are selected species, they're not putting a lot of care into taking care of their offspring. It's just like, get as many eggs out as possible. And then K-selected species, which is they're kind of on a continuum. Like, there's a lot of organisms that are somewhere in the middle, not like just a category, but more of like a spectrum between R and K. And K-selected species are species that reproduce later in life. They have fewer offsprings, are often bigger. They have longer lifespans. These would be large mammals, whales, humans, birds of prey, and long-lived plants. They can be vulnerable to extinction because we don't have a reproductive rate that's super high. Let's see. Some of the traits of each of these types of organisms. Reproductive potential for R-selected is high, for K-selected is low. Population growth rate, it happens really fast for R-selected and slow for K-selected. Time to reproduce or to reproductive maturity, it's short for R-selected species and long for K. Number of reproductive cycles. Lots of reproductive cycles. I gotta move. For R-selected and few for K-selected. Number of offspring, lots for R-selected and few for K-selected. So you can go down that list. You got the idea. All right. A case study that is pretty famous in population studies, especially for animal populations, is about white-tailed deer population in the United States. In the 1900s, deer habitat was destroyed, and there was uncontrolled hunting, and deer populations were dropping, and hunters weren't happy about that. Between the 1920s and the 30s, there were some laws put in place to protect deer. Current deer populations have had explosions in suburban areas. There's been increased deer and vehicle collisions and an increase in Lyme's disease because they need something to keep the population in check, and then various methods to control the deer population have now been put in place. And the other side of this is that we hunted a lot of the deer predators, and so that's been the side of it that isn't great. Okay, that's a white-tailed deer there. The science focus piece is on the southern sea otters and the future of California's sea otters. Factors in a declining sea otter population are increased predation by orcas, because they're a food source. Toxic algae and pollutants that are released into the ocean, like if cultural eutrophication, and we get this toxic algae bloom because there's extra nutrients. They do have a low reproductive rate and a rising mortality rate. Oil spills and fish trapping are also threats that they face. An otter population, though, has been rising in the last several years because these were some of the things that we had to combat. There's another weird one is that cat cat toxoplasmosis. It's a what's it called? Cat parasite. It travels by cat poop. So people would like flush cat poop, like scoopable, flushable. And in California, that's a no-go. Like, don't flush your cat poop because it wasn't dying in the water treatment system. It's getting back out into the waterways, and sea otters were getting sick from it. Species show different patterns of survival from the time that they are born or hatched or whatever it is. There's a pattern that you're going to learn. I want you to be aware of this survivorship curve. This shows the percentages of members of a population that survive at different ages. Late loss means like most of the babies survive, and then there's a drop off later on in life. This is going to be a K-selected species pattern. Early loss is a R-selected species pattern, and then there's a constant loss as well. We'll take a look at those right here. We're going to do the bubble lab, and these are what we're going to actually graph and try to see. This is a logarithmic graph, which means that if you look at the y axis, there it's a tenth, and then 1, and then 10, and then 100. It means that these numbers are so like vastly different that when you graph it, it doesn't make a lot of sense. So we kind of like squish it down into a logarithmic graph, and so it's by magnitudes of 10. And you can see these different patterns. The early loss, those are K-selected species. Constant loss, we usually refer to these as type 1, 2, and 3. As type 1, I think, is our K-selected species. I think that's us. And then 2 are the constant loss, and 3 are the early loss. Don't quote me on that. We'll have to look that one up. Yeah, I think it is in your Fast Track 205. Okay, fastest lecture ever. Are you proud of me? I'm going to post it. Bye, guys.